Okay, so we would continue with the Bjt Dc analysis. So we have seen a lot many configurations, and the entire objective or the entire problem was to figure out the output current and the output voltage VCE. So IC and VCE, what is the IC and VCE in the network, that we needed to solve. In most cases, sometimes the load current was not IC but IE in some of the configurations, but as we know that IE and IC are almost the same, so we can, in a general sense, we can say that the objective of DC analysis is to find out the IC and VCE, the Q point, IC VCE of the particular circuit. So if you are given any circuit, whatever be the arrangement, so we have only considered a few special arrangements which are more popular, but given any circuit wherein one transistor will be there, so you can go ahead and try to find out IC and VCE of that circuit. That is the DC analysis. And what we have to keep in mind, that during the DC analysis we are making a DC equivalent circuit in which we are making all the capacitors open circuit. Inductors will not be there, but if there is inductors, then those will be short circuit. So that is the thing about DC analysis. So we would go ahead and do some more DC analysis with multiple BJT networks. So till now we have only seen networks where we have only a single BJT, but now we will see networks where there are multiple BJTs. So let me share my screen. I hope you can see this multiple BJT networks. So the first one is called RC coupling. So it looks a very dangerous sort of a network with so many elements and all, but simply you can figure out, if you if you observe it closely, that there are basically two voltage divider networks here. So this is one voltage divider network, this side, not till this, but till here. So there is this voltage divider network here, and one more is here. So two voltage divider networks are side by side, and they can be supplied with the same voltage source VCC. So we don't have two different voltage sources in this network, but a single same voltage source VCC is used, and these are joined together. So you see the output side, which is the output side of the first voltage divider network. So this point, the VC point, is connected to the VB point. So here the VC point of the first network, this is the VB point of the second network. So the output signal is going to the input of the second network, but these are connected through a capacitance. This makes all the difference because it is not directly connected. So what happens, because the capacitance acts as an open circuit for the DC voltage, so the DC bias at this point is not affecting the VB voltage. So this VC and VB, the DC voltage VC and the DC voltage VB, are independent of each other. Now you look here in this side. So this is the circuit that you get from here. If you remove all the capacitances, you get this circuit. And so you make this capacitance open circuit, so this RL and RS also vanish from this network. This is the network that you get. What happens here in this network, there is some Q point Q1, as you can see. So this Q1 will have some IC1 and VCE1, and there is another Q2 which will have its own IC2 and VCE2. The DC levels of these two networks will be different, and they will be set by these resistances. The values of these resistances will set the DC levels of these two voltage divider configurations. Now you can see here it is R1, R2, RC, RE are the same here, but you can like consider them to be different also. There is no problem. So the DC levels will change. What will happen? So why are we connecting these two voltage divider networks? What is the purpose? The purpose is that this AC signal that you can see here, this AC signal at the output will get amplified, because this will work as an amplifier. We have not yet discussed the working of the amplifier, how it actually amplifies the AC signal, but just take my word for it. What happens is that the AC input signal will get amplified at the output. Now this AC signal will come to the input of this second network, not the DC. The DC does not come, but the AC comes. Why? Because for the AC, this capacitor acts like a short circuit. So the AC output signal comes here as the AC input signal of the following network, of the second network. And then there is another stage of amplification. So what happens? The amplification is multiplied. So if there is an amplification of suppose A1 in this particular stage and A2 in this particular stage, then the net amplification will be A1 and A2. We can gain on the amplification. So maybe one transistor is not able to supply this total amplification, but we can make coupling like this. This RC coupling we can make, so that we can have we can gain on the multiplication. We can scale up the this amplification. Okay, so this is the purpose of the RC coupling network. So as you can understand, there can be other like multiple stages of this this network. So you can have another network starting from here, actually in this part, another voltage divider network you can connect using this CC. So in this manner you can keep on connecting these networks. So the beauty of this is that each important fact is that each DC level is independent of the other network. So the first voltage dividers DC level and the second voltage divider DC level are independent of each other, though they are connected. The connection is for the AC signal. Actually the AC signal is flowing from one network to another, but the DC is not. This is important to note here. The second multiple Bjt network is very important connection, very important configuration. This is known as the Darlington pair. It has been given a specific name, I think based on the inventor. So this is called a Darlington pair. What is happening here? Here you see that two BJTs are connected in this manner. So the collectors are made common. So the collectors are connected, these two collector points are connected, and the emitter is passed on to the base of the second of the second transistor. Okay, so the emitter of the first transistor is passed to the base of the second transistor. Of course, we need to give a supply voltage, to the base of the first transistor through some resistance RB, and at the output, here the output is not the output resistor or the load is not in the collector side but in the emitter side. So the emitter is having this RE, and there can be some RL connected through some capacitance. But as you know, when we do in the DC analysis, this part of the network and this part of the network are not there. We are only considering this part, and if we see here this one, we can have this is the DC equivalent circuit, and now we analyze this DC equivalent circuit to understand what is the Q point. Okay, so you see here the final load current is this. The final load current is this IE. This IE will be equal to IC2. Okay, so we need to actually find out this IC2. So how to go ahead with this? IC2 will be your beta times IB2. So we need to find out IB2. Now IB2 is basically IE1. IB2 is basically IE1, and which is basically equal to IC1. So there is an IC1 also, but IE1, I think yes, it has a direct relationship with IB1 also. It's like beta 1 plus 1. We know this gamma parameter it can be taken. So it is IB1. So you see IE1 equals to beta 1 plus 1 IB1, and that is equal to IB2. Now IE2 is found out directly from IB2 like this. So IE2 becomes cumulatively this much. Now since we can suppose that this cumulative Darlington pair gain, so we can say that there is a Darlington pair gain beta D. So this beta D will be approximately equal to beta 1 beta 2, because the other terms will be very small compared to beta 1 beta 2. So we can approximate it as beta 1 beta 2, but you can also keep it like this, so there is no problem. This is just an approximation. Now what we need to find out, basically we need to find out the IB1. We need to find out the IB1, because this IB1 is the input base current which we need to figure out in order to get to IE2. So what would be IB1? IB1 you can see here, if we use the KVL in this loop, we use the KVL in this particular loop, then VCC minus IB1 RB minus VBE1 minus VBE2 minus IE RE IE2 RE will be equal to 0, and we have a relationship between IE2 and IB1. We use that, and this VBE1 drop added with VBE2 drop, we can denote it together as VBD. So as if this is a single, these two transistors together make a single transistor, as if it makes a single transistor, and in that single transistor the VBE drop is denoted as VBD, and that is equal to VBE1 plus VBE2. So we use that, and we use this KVL, and we simply would be able to figure out that IB1 would be this one, this much. IB1 will be this one. Okay. So now this is some other facts, like IC2 is almost equal to IE2, which is beta D IB1, and if you want to find out VCE2, so this is the output voltage VCE2 that we are concerned with. So VCE2 will be VCC minus IE2 RE. Yeah, this is IE2 basically. VCC minus IE2 RE, that would be VCE2. So we get IE2 and we get VCE2 in the Darlington pair. So this is how to solve the same way we are solving all the different networks. We have employed the same strategy. We have to figure out what is the output current and the output voltage. For that, whatever we need to do, we have to do that, and we have to utilize the different gains, alpha, beta, gamma, do some approximations. So the approximations are something which you can remember. So as you will observe what sort of approximations we are doing. So these are the approximations you can employ in other configurations also. Some random circuit you may be given, you can employ this sort of approximations. So if some quantity is very large than the other terms, then you can neglect those other terms. The next configuration is a cascade configuration. In the cascade configuration, what happens, the emitter current is the emitter is connected to the collector. Okay, the emitter is or we can say that this is the actually Q1 and this is a Q2, and I think this is the load current that they have considered, IC2 as the load current. So this is the first transistor, this is the second transistor. So the collector of the first is connected to the emitter of the second. In this way it is done, and there are all these capacitors you can see, but when we are doing the DC analysis we have to neglect all these things. So the circuit, equivalent circuit, looks like this, and here we can observe that we have to find out this IC2 and this if we observe that there is some approximation we have to first employ. The approximation is that these currents IR1, IR2 and IR3, all these currents are almost equal, because they are much greater than this IB1 and IB2. IB1 and IB2 are very small, so that's why you can employ the approximation that IR1 and IR2 and IR3 are all same. So when we employ this approximation, then this part becomes a voltage divider. So then we can figure out what is VB2 and VB1 very easily, and that is what we have done here. VB1 and VB2 we have found out by using the voltage divider rule, and then we can find out what is the VE1 and VE2. Then we find out VE1 and VE2. VE1 would be VB1 minus VBE1, VE2 will be VB2 minus VBE2. We get these two voltage levels with respect to the ground. Once we get VE1, we can get IE1. Once we get VE1, we can get IE1. And all these currents, since this is taken, this current, as you can see, this current IC2 is approximately equal to this current, which should be approximately equal to this current. So all these would be equal to IE1, and IE1 we can calculate as VE1 by RE. So all these other currents, all the collector and the emitter currents are same, and we get all these currents. So here we are first finding out the collector or the emitter currents, and then if it is asked, you can find out the base currents by simply dividing with the gain beta 1 or beta 2. Okay, both the base currents will be same because IC1 and IC2 are assumed to be same. Are not same, but like scale like by beta 1 and beta 2. If beta 1 and beta 2 are same, then the IB1 and IB2 will be same. So this is okay. So what else we need to find out? So VE2 is VC1. VE2 we have already found out when VC1 is exactly the same as VE2. We have to also find out VC2. Then we can find out this VCE of the second transistor, VCE of the first transistor. So VC2 we can find out now. VC2 would be VCC minus IC2RC, simply that much. VCC minus IC2RC. IC2 we have already figured out. So this we can also calculate. So in this way we solve the cascade configuration also. So in these configurations you see, when we only accept the first configuration, which is RC coupled, in RC coupled the DC biasing or the DC Q point remains same for each of the transistors, but in the other configurations there is a effective Q point or a cumulative Q point that is emerging out. Okay, so the DC level is getting affected in the other configurations by using multiple Bjt networks. Next one is called the feedback pair. In the feedback pair, what is interesting to note is that we use a NPN along with a PNP. So both PNP and NPN transistors are used. Both PNP and NPN transistors are used. I hope by now you are able to identify which one is the PNP and which one is the NPN by looking at the symbols, the direction of the arrows. Can anyone tell me Q1 is PNP or NPN, or Q2 is PNP or NPN? Right, very good. So I think that I had some small memory tablet for that, like not pointing in and pointing in, something like that. So this is not pointing in, so that is NPN, and pointing in is PNP. So in that way you can remember. And here what is happening, this is connected again, this is almost connected in a similar fashion as the Darlington pair. You see in the Darlington pair how it is connected, and in this feedback pair how it is connected. The connection is same, but the difference is in Darlington pair both are same type of transistor, either NPN or a PNP. Here one is NPN, another is PNP. That is the difference. Now this is all it takes to change the DC levels of these two different feedback connections. Darlington pair is also a feedback connection, but it is called Darlington pair, whereas this is called specifically called feedback pair. Now here the DC equivalent, as you can see, the DC equivalent circuit is this, and let us now analyze the DC equivalent circuit. So first we have to find out, we can actually find out the various relationships. So this is a collector current is here. Now the collector current, the collector is connected to the emitter. In this case the collector of the PNP is connected to the base of the NPN. So the collector current of this first transistor would be beta times the base current. So IC1 equals to beta 1 IB1, and that is equal to IB2. That is equal to IB2. So this relationship you are obtaining, and then IC2 would be beta times the IB2. Now these betas are different. So first one has beta 1, second one has beta 2. So effectively IC2 would be beta 2 beta 1 IB1. IC2 is this one, beta 2 beta 1 IB1, and IE2 is almost equal to IC2. So this is the current that is passing through. Now that is fine, but what we need a load current IC. IC is not equal to IC2. IC is IE1 plus IC2 or IE2, the same thing. Okay, so we have just noted it like this, IE2. So this would be equal to beta 1 IB1, because IE1 is almost equal to IC1, and that is beta 1 IB1 and plus beta 2 beta 1 IB1, and hence we can write it in this manner. And again we employ the approximation. We again employ the approximation and we neglect this term because this is much smaller than this one, and ICs becomes simply beta 1 beta 2 IB1. Okay. Now, okay, so IB1 is something we need to find out. We have not yet found out what is IB1. All the other currents we have found out in terms of IB1, but IB1 we have to find out. For this we employ this KVL. The KVL here we employ. So VCC minus ICRC minus VEB1. So this is the emitter, this is the base. This is the emitter, this is the base, this is the collector. And we are coming from E to B. So EB1 minus VEB1, okay, minus IB1 RB equal to 0. So IB1 will be like this, VEB1. So just tell me one thing. When we come from B to E in a NPN transistor, B to E, we have positive in B and negative in E. Here in the PNP we have negative in B and positive in E, right? So VEB will be VEB when we are going from this side to this side, that will, we have already included the minus sign here. So VEB will not be negative, it will be a positive quantity. Okay, so effectively this is VCC minus some quantity. And what else? We can calculate VCE2 and VEC1. VCE2 we can calculate and VEC1 we can calculate. VCE2 is simply VCC minus ICRC, that is also VC2, and VEC1, see this VC2 is this same point, so VC2 minus VC1, VC2 minus VC1, and VC1, this point VC1 is, this is 1, VC1 is same as this potential VBE2, VC1 is same as VBE2, so, and VC2 is same as VCE2, so VEC1 is VCE2 minus VBE2. So all these are, you do not need to remember anything, okay, but you just try to follow the analysis. Don't need to remember anything, just try to follow the analysis. If you are observant, if you are able to look into the circuit closely and figure out where which points are same, where there is a drop, all these things if you are able to carefully observe and carefully note down, then circuit solving is nothing very difficult. Okay, you just need to spend some time observing the circuit. Don't just rush into the circuit. Whenever you are given a circuit, don't just rush into solving the circuit. But spend some time, 30 seconds to 1 minute you spend seeing that, to see the circuit closely, carefully. Identify the different points which are same, the different the points where there is some resistance is connected between those points, so there will be a drop. So identify all these things in a circuit, then go ahead solving the circuit. I think this is the last one for the multiple configurations, multiple BJT configurations, direct coupled. So in direct coupled, in art it is voltage divider network which is connected to a second transistor directly. Okay, it is not connected through any RC coupling or anything. It is direct coupling. Direct coupling. That is why it is called direct coupled. So you see the equivalent network. The first stage is a voltage divider network, so you can solve it in that manner, voltage divider network, and whatever you find out this VB2, that is going this VC1 which is the collector potential of the first BJT, that is the same as the base voltage of the second BJT, so that is VB2. And when you find out VB2, you can get IE2 also. Okay, you don't need to find out exactly what is the IB2 current here in this case, because this one is connected as this one is base bias in that form, it is connected. So now how to go ahead solving? So this IB1 we have to find out, this IB1, because this is a voltage divider. So this IB1 we find out by making that again Thevenin's equivalent circuit. So we employ the same idea of Thevenin's equivalent, looking from this side. So there will be an ETH and VB1, ETH minus VB1 by RTH plus beta 1 plus 1 RE1. So this RE1 would be reflected to the input side. As if you remember, it gets reflected by multiplying itself with gamma, beta plus 1. It gets multiplied with gamma and gets reflected to the input side. So RTH plus beta 1 plus 1 RE1. So you can employ these equations straight away if you remember. Otherwise, you have to again go ahead and figure out what is the Thevenin's equivalent and Thevenin's equivalent ETH, RTH, and also understand why this beta 1 plus 1 this is scaled up by beta 1 plus 1. So all those if you have to do if you don't remember this formula, but this is very easy thing actually to note down. Whenever there is a emitter resistance, that emitter resistance appears to the base current as scaled up by beta plus 1 times. This you remember. This is a very important thing you can remember. This will ease your life a lot. So the emitter resistance appears to the input current to be scaled up by beta plus 1. Okay, so that is the thing. Now this we have already solved before. RTH is R1 parallel to R2 and ETH is this R2 by R1 plus R2 VCC, and we employ all these values and we find out what is IB1. We can easily get IB1 now, and once we get IB1, IC is obtained. IC is obtained because IC we can straight away write that as beta 1 plus beta 1 IB1, because we are having an assumption that IC is almost equal to IC1. So this assumption has not been stated here explicitly, but we can understand IC is almost equal to IC1 because the IB2 is very small, that's why. So IC is almost equal to IC1. So we have been able to calculate IC as beta 1 IB1. Then VB2 we can calculate, that is only the drop we have to subtract from VCC. Then VE2 we can calculate. VE2 is what? This much here. So VE2 is this VB2 minus VBE2. VB2 minus VBE2. So this VB2 we have already found out from here, and we again subtract VBE2, we get VE2. IE2, which is a load current now, IE2 is the final load current here, which is VE2 by RE2. And if you want to get the VCE2, the output voltage of the transistor, final transistor, this is simply VCC minus this voltage VE2. VCC, this point is VCC directly connected to VC2, minus VE2 is what is giving you VCE2. So all these circuits can be solved in this manner. So any question till now? All we are doing is solving the circuits like step by step, just observing from which point we have to start and going ahead one by one, employing some approximations. Sometimes you will find that the approximation, if you don't employ, then also you can solve, but we employ the approximations to make solutions easier, that's all. Okay, so the next one is also a multiple BJT configuration, but this has a unique name, or it is also like an application actually. So this is called a current mirror. This is called a current mirror. Here what we do, these two are identical transistors. This Q1 and Q2 are identical transistors in the sense that they employ the same beta, so the current gain is the same. Okay, so and because they are identical transistors, another important fact is that VBE IB characteristic, the input characteristics, is also the same. Input characteristics is also the same for both these transistors. Now with that understanding, now you look into the configuration. In the configuration you find that this is one transistor and this is another transistor. The bases are connected together. The base are connected together and the emitter side is grounded. This means that this potential, base potential, is same for both the transistors all the time. The base potential is tied up together. So this VBE2 and VBE1 are the same always. Okay. So if these two are same, by the input characteristics for a particular VBE, the IB is getting fixed from the input characteristics. Since the input characteristics are same for both the transistors, the IB1 and IB2 are also becoming same. I hope this point has gone across. So I repeat once more. So here you see, by the configuration, the bases are tied up together and the emitters are grounded directly. So VBE1 and VBE2 will be same all the time. Now these two transistors are identical, so they employ the same input characteristics. From the input characteristics, for a particular VBE, the IB becomes fixed. So the IB for both the transistors is also same, because the VBE is same for both the transistors. So IB1 and IB2 becomes same all the time. And now you see what is IB. IB is IB1 plus IB2. What are we applying? KCL or KVL? KCL we are applying here. So from KCL, IB equals to IB1 plus IB2, which is twice IB1, because these two are same. Now this IB here, which is flowing here, now I control, this control current I control is IC1 plus IB. Now IC1 is beta times IB1, IC1 is beta times IB1, and IB is twice IB1. So what we get is beta plus 2 times IB1, which is almost equal to beta times IB1. So the I control is almost equal to beta times IB1. Or one can also say in other way, IB1 is I controlled by beta. In this way you can also say. Now notice that IL, the load current is IC2 directly equal to IC2. There is no branching coming from here. It is directly equal to IC2, and IC2 is beta times IB2. Now IB1 and IB2 being same, the load current becomes same as the control current. Of course, exactly if you do the analysis, there is some difference because control current is beta plus 2 times, whereas the load current is beta times. But approximately we can neglect that very small difference, and we can say that the load current is same as the control current. Load current is same as the control current. Okay. And there is also a built-in control in this particular configuration. If the IL changes, what happens? Your IC gets changed. IC is changed, right? So let me just go through this. Suppose your IL is increased. IL is increased. If IL is increased, IC2 is increasing because IL and IC2 are same. This is increasing your IB2. Why? Because IB2 is IC2 divided by beta. Beta is constant. IC2 is increasing means IB2 is also increasing. When IB2 is increasing, what is increasing? VBE2 is increasing. VBE2 is increasing. Now this VBE2 is same as VCE1. Did you note this? I think you haven't noted this till now. This point is taken to this point by this connection. This point is taken to this point. So VBE2, this potential with respect to ground is same as this potential with respect to ground. But this ground is in emitter. So the VCE1 is basically equal to VBE2. So VBE2 increasing will also make VCE1 increase. When VCE1 increases, what happens? This I control will decrease because I control is nothing but VCC minus VCE1 divided by R. We have not changed anything in R. Now VCE1 has increased suddenly. So I control is decreasing. I control decreasing means I control decreasing. Let me write I control. I control decreases. I control decreasing means IB1 decreases. IB1 decreasing means VBE1 decreases. VB1 decreasing means this VBE2, which is same as VB1, will also decrease, and this will again pull down IB2, which will again pull down IL. So if for some reason, due to some fluctuation in the load, IL tries to increase, then the configuration itself will again act in such a way that it will pull down IL to whatever value it was having. So there is an inherent feedback control acting in this configuration. Similarly, if IL tries to decrease, the network will again push the IL up. So it will maintain the load current. there is a built-in control here, it will maintain the load current. Did you understand this one, or do I need to repeat? I hope this is okay with you. So this sort of analysis sometimes is required. Okay, this up down analysis, this is called up down analysis. And don't think that this is happening in steps, that first there is some duration when IL will increase, other quantities are fixed, then IB2 increases, other quantities are fixed, then VB2 increases. It doesn't happen in this way. This entire action happens at the same time. All of this happens at the same time, because this is an analog circuit. Everything happens simultaneously in a continuous fashion. There is no stepwise operation. The operation is in continuous mode. So all these things happens at the same time, which means that you will not even notice, or you may notice a very slight change in IL, and it will again come to its position, come to its whatever load current had been fixed. And the load current is getting fixed by the control current. Remember this. So we have a very nice control over the load current. So irrespective of the load, we can deliver a current to the load. So you can change the load, but we can keep on delivering the same current, and the current will be same as the I control current, and this I control current can be changed by changing this R. Once you fix this R, you have fixed the I control. Now you can forget about it, and the IL will remain same as I control, and any fluctuation in the load side will not cause any fluctuation in the load current. So this is the beauty of this network. Very robust configuration is called the current mirror. Okay, how many things are we having? Okay, I will end with constant current source. I thought of finishing all the other points also. Let me see, this is very small things actually. Let me see if I can cover also. So this is constant current source. How we have configured it, you see, this is a I think, I don't remember also the names, but I think this is the base bias or the common base configuration maybe. So here what we have done, we have connected a zoner diode between the base and the this point and the end of this resistance, RE resistance. We have connected a VZ. So what happens is this, that when this zoner diode is conducting, that time in this loop you have, this is the KVL, VZ minus VBE minus IERE equal to 0, and then your IE, which is the load current, will become equal to VZ minus VBE by RE. This current becomes independent of this resistance R1 in this side. Okay, is only, so the potentials VZ and VBE are very fixed potentials, and RE if you can fix, then this current IE is getting fixed, and this IE is equals to the I current, which is the current we desire to drive. This is the constant current, and if we have any load circuit attached at this point, from this point if you have any load circuit, this will experience a constant current I. So we have been able to create a constant current source, so this will be equivalent to a constant current source connected to a load. This entire part becomes like a constant current source, this one. And this Vz, how can we ensure that the Zoner diode is actually in conduction? Because we have placed this negative potential, this you can see very easily that this Zoner diode is reverse biased. Zoner diode is reverse biased, so there is a current conducting through the Zoner diode, and hence the potential drop across the Zoner diode remains constant, and thereby the current becomes very constant. So I think this much is fine for today. We will start again with the other, we will cover the remaining topics tomorrow, and we will also start with AC analysis of BJT, AC analysis of bipolar junction transistor networks. So in AC analysis, what we will be doing, we will be now introducing a AC signal at the input side, and then due to the AC, we have to formulate the AC equivalent circuit and then solve for the different variables that would come into picture in the AC. So we will explain that next day anyway. So this is fine for today, and any questions, any doubts? I hope now DC analysis should be very easy for you guys, and I think that tutorial has already started for the DC analysis of BJT, and practice a lot of problems. The books have been already referred, so there are a lot of solved examples in the books also, and you also read the books for getting the finer points. It is not possible to discuss all finer details in the class, as I have mentioned earlier also. I am only presenting that much which is very much essential, the fundamental things, but to know more, if you have more interest in electronic circuits, you have to go to the book, you have to read the book by yourself. Okay, so if you don't have any questions or queries, then I will end the meeting, then end this lecture. Okay, thank you.
Thank you, sir.
Okay.